and I will share screen, and then we can get started. Okay, that's not the right thing. I think we want topics in model theory. Which is here. Okay, cool. So are there any questions before I get started about Ramsey classes of finite structures or about generalized indiscernibles?
I have a question. So when we first defined a Ramsey class, in the definition we specified that the elements should be rigid, and
Yeah.
we didn't mention that last lecture. So when proving something with Ramsey, we didn't quite mention rigidity.
Yeah. So I should have. I
was
didn't.
thinking that in Scow's theorem, it seemed like more important that we need rigidity of the elements. Because I was
That's right.
thinking that maybe for indiscernible sets don't seem to have the modeling property.
That's right. So also, I mean, structures that, I mean, so what we want to do is we want to sort of identify structures with tuples that enumerate them. This will come up in the proof. And if you have like a linear order in the language, which is what we will assume, then there's a sort of unique way of doing that, like a canonical way of associating a tuple to a structure. Namely, you can give it its increasing enumeration. And you can sort of identify things that way. But if if you don't have a linear order around, then you don't have a canonical way of doing that. Now, one thing that you can prove, and this is an easy consequence of the Kekkers-Pistov-Todorcevich correspondence, is that if you have a Frisé class consisting of rigid elements, then if it's Ramsey, it has a definable linear order. So it's not, rigidity will come from a linear order. I mean, it could come from other things, but it's sort of like without loss of generality, you can assume that you have a linear order around, and so that's what we will assume. But I should have said that this rigidity assumption is going to be like a built-in assumption for the Ramsey stuff that we do. So it's a good point. Were there other questions? No? Okay, then let's go ahead and dive in. So last time, we talked about Ramsey classes of finite structures. So let's just recall the definition. So, oops. So to be Ramsey, you have K is Ramsey if K is a Frisé class. And for every A contained in B in K, and R less than omega, there exists some C also in K, such that C arrows B, A, R. And let's just remind ourselves what that means. You find some C so that if you color all the copies of A sitting inside with I don't know, R many colors, whatever R may be, then no matter how you color it, you can always find some copy of B sitting inside in which all of the A's get the same color. And such a B is called homogeneous for the coloring. Okay, so C is probably huge. I mean, it might need to be very, very big to be guaranteed that there's going to be some monochromatic B living inside. But if you're in a Ramsey class, then you can always do that. Now, the classical Ramsey theorem, and you should give yourself this as an exercise if it's not clear, the classical Ramsey theorem can be seen to be equivalent to saying that the class of finite linear orders is a Ramsey class of finite structures. Another remark that's worth making is that you can sort of restrict to being a for say class, because if you have a class which has the hereditary property and joint embedding, then this Ramsey property will imply that you have amalgamation. It'll imply that you're a for say class. So the amalgamation property is actually a consequence of having this coloring property, which is worth knowing, although I won't give the proof. Okay, so can everyone hear me? So there's a comment in the chat that okay, good. So as long as it's not a generalized problem, then I think we're fine. Great. Okay, so one comment that I want to make also is that the following is a consequence of like an easy induction. So suppose we're given a0 through an minus 1, which are contained in some b in k, and r0 through rn minus 1 in omega. Then if k is Ramsey, that's not a k, let's try that again. If k is Ramsey, there is a c in k such that there exists some b prime. Well, okay, let me say it this way, such that given colorings chi I, which color copies of ai living inside of C, there exists some B prime, which is a copy of B living inside of C, such that chi I restricted to the copies of, sorry, that's B prime, of AI and B prime is constant for all I. So the idea here is, maybe I have finitely many structures that I'm given. Separately, I color the copies of each. So I have two structures, let's say. I have A0 and A1. And I color all the copies of A0 with one coloring, and I color all the copies of A1 with another coloring. And I want to find some copy of B such that all the copies of A0 get some constant color and all the copies of A1 get some constant color. Okay, how can I do this? Well, this follows by induction. Why? Well, for the case of n equals 1, it's easy because that's just the Ramsey property, right? Then I only have one coloring. Now, suppose for induction that I can do it for n of them. And now I'm given n plus 1 structures. Well, the Ramsey property tells me that I can find, first induction tells me that I can find some C0, such that if I look at the first n colorings, I can assume that there's some copy of B living inside, so they all get the same colors. And then I can find some copy of, I can find some C, such that in some copy of C0, all the ANs get the same color, and now everything has the same color. So I encourage you to try to do this induction. We drew a picture of it last time, but I just wanted to make this fact explicit because we will use it in the upcoming proof. Okay. Now, let's do the theorem. Okay, so here's the theorem. And this is due to Lynn Scow. It's a fairly recent theorem, I think maybe 2012, 2013. And what it says is that suppose I is a uniformly locally finite L prime structure in the finite language L prime, such that the age of I, which we'll call K, is a Frisé class. Then I indexed indiscernibles have the modeling property if and only if K is a Ramsey class. And we will say I forgot to include this assumption. Let's assume, let's say I expands linear order. So that's an assumption we'll need. So I'm sorry for including it at the end. What we'll need to assume is that part of the language of I will contain a linear order symbol, and I will be linearly ordered by it. So I expands linear order, so maybe with additional structure, but that'll be a baseline thing. Okay, so if you have some index model that expands linear order and its age is a Frisé class, then I index indiscernibles have the modeling property if and only if K is a Ramsey class. That's a correct statement. Now, what does this say? Let's recall what the modeling property said. From the very beginning of this class, we were interested in finding indiscernibles that somehow closely resembled a given sequence, right? We started with some infinite sequence. We wanted something that closely resembled it. And the way we encoded that was we wrote down some EM type. And what did the EM type say? These were the formulas that were somehow true, regardless of which increasing in tuple you picked. Now, in general, with generalized indiscernibles, instead of looking at each increasing in tuple and which formulas are true for all of those, you look at each quantifier-free type inside the index model. And you want to know what formulas are true, regardless of which realization of the quantifier-free type I take. And then those formulas should still be true of something locally based on the sequence. And another way of saying that is that whenever you have something that's true of the indiscernible sequence, there's some something from the original sequence whose index realizes the same quantifier-free type that satisfies that formula. These are equivalent. So okay, now our goal is to do this. And the interesting part of this theorem is not that the Ramsey property implies that you have indiscernibles. That's maybe not so surprising given the way that Ramsey's theorem enters the picture when you want to prove that indiscernibles exist. The interesting direction is that it's somehow equivalent. So it tells you that there's a kind of dictionary between generalized indiscernibles and Ramsey classes of finite structures. And then just one more comment is that I here is not required to be the Frisé limit. So I is a structure whose age is K, but it doesn't have to be the Frisé limit. I does not need to be homogeneous. So an example to have in mind is K could be finite linear orders, and then I could be the natural numbers. So the natural numbers don't have any automorphisms as linear order, but their age is the class of finite linear orders, which is a Frisé class, whose Frisé limit is, say, the rationals. Okay, so let's prove this. All right, so let's do modeling property implies K is Ramsey first. And this direction is kind of fun. Okay, what do we want to do? We want to cook up a sequence, take something which is locally based on it, and use that to conclude that I is Ramsey. So what structure will we take? We'll take I itself, or a certain expansion of I itself. So let's see how to do this. So by last time, it suffices to show that if A contained in B, in K, and R is less than omega, then I itself arrows BA sub R. Recall that last time we had this argument that said being Ramsey for the class is equivalent to saying that actually if you colored all the copies of A in some infinite structure whose age is K, that you can find some B. So this was equivalent. This was the kind of ultrafilter compactness argument that we did last time. Okay. Now, since I expands linear order, we may identify A with a tuple little a, giving the less than I increasing enumeration of A, and likewise for each A prime in, or sorry, that should be an I. That should just be an A. Okay. So, okay, we can identify each structure with the tuple that gives its increasing enumeration. So we can worry not about the structures, but rather about tuples. This is just a reduction. Okie doke. So what we'll do now is we'll fix a coloring. Chi, which will color copies of A with R many colors. And now we want to find a B living inside of A. So how are we going to do that? Well, we'll let N be the size of A, some finite structure, and we will let L be a language with n-ary relations R0 through R sub R minus 1. M will be the structure whose domain is I, and the interpretations are, we interpret Ri in M to be the tuples, oh, that's weird, J bar, such that J bar satisfies the quantifier free type in the language L prime, the language of I, as A, and chi of J bar equals I. Okay, so what's going on here? Well, first off, when I say that I have a tuple J bar that realizes the quantifier free type of A, because it realizes the quantifier free type of A, J bar enumerates a structure which is isomorphic to A. J bar enumerates a copy of A inside of M, or inside of I. That means that I can plug it in to the coloring. So when I write chi of J bar, I really mean chi of A prime, where A prime is the copy of A enumerated by J bar. And RIM will hold of that tuple just in case the tuple, or the structure it enumerates, gets the color I. So these predicates are coding the coloring for you. To know which structures get the color I just look at which tuples fall into the predicate R sub I, or the relation R sub I. Does that make sense? So this is a structure now which encodes the coloring, and that's it.
So Nick, just small a is the enumeration of capital A, right?
That's right. Yeah. So that's exactly right. So I said that here with the tuple A. Exactly. So A here is the tuple that enumerates the structure capital A.
Thank you.
Which is finite structure. Yep. Okay, cool. So this now gives us a structure, and we will consider AI, I in I, which is a collection of same length tuples in M, defined by AI equals I for all I in I. So now I have a collection of tuples indexed by I, where everything is the element that it indexes. Okay, so this is the collection of tuples, and now we want to find something which is indiscernible. So by the modeling property, there is, in an elementary extension, of M, some I indexed indiscernible bi, I in I, which is locally based on AI, I in I. Now, here's one thing to notice. Inside this indiscernible object, whenever you take something that satisfies the quantifier free type of A, they all have the things that they index have to have the same type. That's what it means to be generalized and discernible, right? That, you know, if you have two things that have the same quantifier free type inside the index model, then the things that they index have to have the same type. So in particular, if I take two things that satisfy the same quantifier free type as A, they have to get the same color in the sense of the predicate, right? I have this predicate that codes a coloring. And, you know, if I take two things that satisfy the quantifier free type of A, then the things that they index have to get the same color, maybe I star. You know, they have to live in the same predicate. And that is going to give us the guess for what will be the homogeneous set inside the original thing. Okay, so now what do we do? So let J bar be the increasing or the less than I increasing enumeration of B. B, recall, is the structure that we want to define such that all the copies got the same color living inside. Now, we know for all I bar, well, let's say it this way, there is some C star, let's say, this is like a color, less than R, such that for all I bar in B, realizing the quantifier free type of A, we have that R sub C star B I bar is satisfied. So this is just what I was saying before. If I take any two things that have the same quantifier free type, they have to live in the same predicate. So RC star is just what we're going to call that predicate. And this just follows by indiscernibility. One thing that I'll mention is you might reasonably ask, okay, why do I know that that it has to satisfy one of the colors? Why does it have to be in all the predicates? But what you know is that in the original structure, the predicates R0 through R minus 1 partition the objects indexed by the quantifier, by realization of the quantifier free type of A. And that means that that's still going to be true in something locally based on it. Like, for everything that realized the quantifier free type in A, you have the disjunction. Either you satisfy R0 or R1 or R2 or R3. Since that's true of all of the realizations of that quantifier free type, it has to be true in the generalized indiscernible. And so one of the colors will be satisfied. And in fact, it has to pick one, which we'll call RC star. Great. So we have this J bar here. So now what we know is by local basedness, there is I bar in I such that the quantifier free type in the language L prime of I bar equals the quantifier free type of J bar, and the type of AI bar equals the type of a J bar, or sorry, BJ bar. This is what local basedness says. It says that whenever you have a formula which is satisfied by something in the generalized indiscernible, there has to be something whose index is the same quantifier free type that satisfies that formula in the tuple, in the collection of tuples you started with. So if I change the index to something that has the same quantifier free type, I can find something that has the same type because the language is finite. So here I have a finite language, so I can just write type. I don't have to say delta type, or I don't have to say formula, because the language is encoded by formulas. Okay, but then every I prime in I bar, like a subtuple of I bar that enumerates a copy of A, i.e. satisfies the quantifier free type of our little a, gets color C star. So we find a homogeneous set. Or a homogeneous structure isomorphic to B, homogeneous copy of B. Namely, the B prime enumerated by I bar. Okay. So because the type of the element encodes the way the coloring behaves, and you know that in the indiscernible, you always had the color C star, then because that had to come from something witnessed in the original sequence, you find something in the original sequence such that all the copies of A that it sees get the same color. And that's exactly what it means to have a homogeneous set. So this direction says that if we have the modeling property, we can find the Ramsey property for the thing indexed. So now we want to go the other direction and give an argument that shows that if we have the Ramsey property, if we have a class that is a Ramsey class, then we can get generalized indiscernibles. So let's do that now. So now let's do. Oh whoa, that's my calendar. Okay, any questions about this argument before we move on? Okay, let me just draw a picture very quickly. So we've got our M, which is a copy of I. And then we have, in some elementary extension, we have like our BIs. And we know that sitting inside the BIs, we had J bar, which enumerates B. And if we look at the copies of A sitting inside, they all have the same color, right? Now, there's a formula in the language that says all of the copies of A inside of J bar get the same color. What do you say? You just look at the conjunction that says for every in elements that realize the quantifier free type of A, the predicate R sub C star holds on them. That expresses that every copy of A living inside of this copy of B get the same color. Now that formula, if it's true of the generalized indiscernible thing, had to be satisfied by something in the original sequence indexed by something whose quantifier free type is the same. So that means that you find some I bar here, and because it satisfies the same type, all of the same elements have to satisfy that predicate R sub C star. But what does it mean for all the things here to have the same, to live in this predicate R sub C star? It means that the coloring gives them the color C star. So what did we do? We had some coloring on all of M, which is I, and we found a copy of B living inside such that all the copies of A get the same color. And that means that we showed that given an arbitrary coloring, we could find a B such that monochromatic for the coloring. That means that it's Ramsey. So that's the structure of the argument.
Nick, that's why you need the language to be finite to write this formula.
Yeah, because you want the quantifier free type of A is a formula.
Yeah.
Yeah, so here you're really using that it's a Frisé limit because it's not just that you need to know that quantifier free types are isolated by formulas. Yeah, but that's a great point. This is really what you use. Okay, cool. So this direction's good. All right, so now let's do the other direction, next direction. So let's suppose that we have a Ramsey class. And now we want to find the modeling property. Okie doke. So we're going to assume now that we're given I, whose age is a Ramsey class K. And we're also going to assume that we're given AI, I, and I. And we want to show that the following is consistent. So I'm going to look at a whole bunch of formulas that express the following two things. So the first thing that we're going to express is that we're I-indexed indiscernible. So how do you say with a collection of formulas that you're I-indexed indiscernible? Well, what you say is you say phi of xi bar holds if and only if phi of xj bar for all I bar and j bar with same quantifier free type, and for all formulas in the language. Okay, so I look at all tuples in the structure. Any pair of the tuples that have the same quantifier free type, I have to throw in this biconditional. It says this is true if and only if this is true. And if that's satisfied, then certainly what you have is I-indexed indiscernible, because two things that have the same quantifier free type index two things that have the same type, because all the formulas that one satisfies are the same as the formula that the other satisfies. That's clear, right? So certainly this tells you that if you realize this collection of formulas, you get an I-indexed indiscernible, but we don't just want an I-indexed indiscernible, we want one that closely resembles the sequence we're given. So now we need to talk about locally based. And for this, we just write down the sort of generalized analog of the EM type. We do exactly what we did before. So we write down the formulas phi x I bar such that for all j bar that realize the quantifier free type in the language L prime as I bar, we have that phi a I bar is satisfied. Or sorry, phi j bar is satisfied. So let's think about why this expresses local basedness. So I want to claim that if I take something that realizes this collection of formulas, it's locally based on the original sequence. So how to see that? Well, suppose you realize these things. And you take some formula, let's call it psi, which is realized by B sub J bar. Okay? Or yeah, B sub I bar. Let's say so you realize by B sub I bar. Now, I know that its negation was not in this collection of formulas. Because if it was, then I wouldn't have a realization, right? Like if I realize these formulas and I satisfy some psi, then that meant that its negation wasn't here. It wasn't in this collection of formulas. Now, what does it mean for the negation of this formula not to be here? It means that there's got to be something, some j, with the same quantified free type that satisfies psi. Because if everything with the same quantified free type satisfied not psi, then psi would go in. So satisfying this is the same thing as being locally based. So, I mean, there are two ways of thinking about this. One is a sort of universal way, and another one is a sort of existential way. So the local basedness idea seems to say it's existential. Anytime you have a formula that's satisfied, there has to be something with the same quantifier free type that indexes a tuple that satisfies the same formula. That sounds existential. But the way that you think about the EM type is you just throw in the formulas that are satisfied by everything, regardless of the quantifier free type you take. And it's easy to see that these are the same just by playing games with like De Morgan's law or no, just actually with contrapositive, negating quantifiers. So, okay, these are the same. So, okay, we've got a big collection of formulas. One of them expresses that we have I-indexed indiscernibility, the other that expresses that we have local basedness. And what do we need to do? We just need to show that these are consistent. Because if we know that they're consistent, then a realization will be the sequence we're looking for. So it's enough to show that this is consistent. And how do we do that? Well, it's enough to show that it's in fact finitely satisfiable in the sequence we started with. Because if it's finitely satisfiable, then in particular, it's consistent by compactness. Okie doke. Okay, so fix any finite collection of quantifier free types in the language of the index model in L prime. We'll call them P0 through Pk minus 1. And let n be the number of variables, like the max number of variables that you see in any of these. All right, now for each I less than k, let ai in our class k be a structure such that if ai realizes pi, then ai enumerates ai. So I should have said that these are like complete quantifier free types. So they determine an isomorphism type of a finite structure. Every quantifier free type in finite many variables does that when you're working with a Frisé class. And in fact, when I say complete quantifier free type, by the fact that you have a Frisé limit, you know that that's in fact expressed by a formula. This is a consequence of the Rilnard-Jevsky theorem. So for those of you that have seen model theory, you know that in Aleph0 categorical structures, if you have finitely many variables, then you have finitely many formulas, each of which isolates a complete type. So I could assume that these are complete formulas, even. This is equivalent. Okay, now we'll let B be an arbitrary L prime, or like an arbitrary structure in K. in K, into which each AI embeds. And what we'll do is we will define a coloring for each I less than K, some chi of, let's say, A prime. Well, okay, now let me say it this way. Chi I, which goes from copies of AI in I to, oh, sorry, so sorry. And one more thing that we have to fix is fix a finite delta contained in the original language. So we have a structure, with the language L. This is where we normally work. And this is where the AIs come from. And then we had a language L prime, which is the language of the index model. So we fixed a finite collection of delta formulas. Sorry. So now we're going to define a coloring, which takes its values here. Now, let me first define the coloring, and then I'll say what all this means. So chi I of A prime sub I is going to be the type in the language delta. Oh, sorry, this notation is very bad. Let's say it this way. J bar prime is the type of A sub J bar prime with respect to the language delta, where J bar prime is an enumeration of some copy of AI in I such that J bar prime realizes the type PI. So, okay, so lots to explain here because much of this is confusing. So for each of these structures, AI, we know that there's some way of enumerating them such that I realize the type PI, right? So whenever I have a copy of AI, I can identify it with a tuple that enumerates it in that way. Like I can enumerate the elements in some way, call them J bar prime, such that it realizes that the associated type. That will index something in the original collection of tuples. And the color that I'm going to assign to J bar prime will be the delta type of the thing it indexes. Okay. Now, this set here, S in sub delta over the empty set, this is complete types in variables using only the formulas delta. Now, what is the size of that set? Well, for each formula in delta, to determine a type, I have to tell you whether to put it in or to take it out. So I have two choices for each formula of delta, and that means that I know that the size of S in delta over the empty set is at most 2 to the delta, which is finite. So finite. So by the remark above, there is some C in K, a substructure, finite substructure of I, such that for every I less than, that's the little k, if I restrict chi I to copies of AI living in C, this is constant. So this is why we needed this remark from before. So remember at the beginning of the lecture, I said you can sort of generalize the definition of Ramsey structure, where now I give you, instead of just one structure, A, I give you n structures, A1 through A(n-1), or A0 through A(n-1). And for each one of those structures, I give you a way of coloring the copies of AI living inside of C. Then you can find a B such that no matter which I you take, the AIs inside that copy of B will be monochromatic. Okay, so now we have our AIs. We find some C. Oh, gosh darn it, I said it wrong again. So we find some C in I such that there exists a B. Goodness, this is really bad form. Such that there exists some B prime in copies of B inside of C, such that chi restricted to copies of AI and B in B prime is constant for every I less than K. That's what I meant to say. Okay, cool. So my mother's dog is very upset that I didn't remember to put B there. Okay, so now we can just take it to the hoop. We're ready. So what do we know about this thing? So what we can do is we can let n prime be the size of B, and we can let j bar prime, or I don't like j bar prime. Let's do capital J bar be an enumeration of B. Then we know that A indexed by j bar prime satisfies the union over all I less than K, the union over all I bar and I bar prime that realize P sub I in B. So this is going to be my notation for realizations of P sub I in B. And what do we have? We have they satisfy phi x I bar if and only if phi x I bar prime as phi ranges over stuff in delta. Why? Well, because what does the coloring say? The coloring tells you the delta type, right? So what I know is I have these finitely many types, and I'm told that on realizations of those finitely many types coming from B, I have constant color. So that means that the types of any two things that realize the same quantifier free type among this collection will end up with the same type, meaning one will satisfy a formula phi if and only if the other does. So they satisfy this. Now, also, a j bar satisfies 2. In the variables xj bar. So what did 2 say? 2, before, recall, this was like our analog of the EM type. And because a j bar comes from the AIs, it automatically satisfies its own EM type. Everything satisfies its own EM type. It doesn't satisfy anything that isn't satisfied by anything in the sequence because it comes from the sequence. Now, so let's call this set star. Now, this depends on delta and on B and on P bar, where P bar is our list of types. Now, every finite subset of 1 and 2, the formulas that we were looking for, is contained in a union of star, delta, B, and P bar for some, well, let me say, and 2 for some delta, B, and P bar. Okay, why? Well, okay, if I take a finite subset of 1, certainly it can only mention finitely many quantifier free types. So that gives you your P bar. Certainly it can only mention finitely many formulas coming from L. So that gives you your delta. And certainly it can only mention finitely many variables. And our variables were indexed by I. So those variables will enumerate some subset of I, which generates a finite structure. Let's call the substructure that it generates B. So I only really need to talk about realizations that have the same quantifier free type, not in all of I, but just coming from some finite B. So that gives me my B, that gives me my delta, and that gives me my P bar. And that's a finite subset. So every finite subset of 1 and 2 is contained in star for an appropriate choice of delta, P bar, and B, and all of 2. And I've shown that that's satisfiable, which means that the whole thing is satisfiable. A realization then gives me my indiscernible that I was looking for. And that's the proof. Okay, so that's it for today. Now, next time, and probably the time after that, we'll prove Shell's second dichotomy theorem. It says that if you have the tree property, you have the tree property of the first kind or the second kind using generalized indiscernibles, and that will move us really into the core material of the class. So are there any questions?
Quick question. So the first capital N you used in the proof, that's the number of variables appearing in the quantifier free L prime types, P0.
Yes, that's right.
So not in delta.
Right. Although it's going to be more or less the same, I suppose, because I want to be able to sub in xi bar into formulas in delta. So I could assume delta has an in.
Thanks.
Okay, any others? No? Okay. Well, this proof was written up, and so I will post that this evening. So you're free to look at the notes then. And I'll try to also have the notes for Shell's second dichotomy theorem written up before I give them, because that way I think it's useful, because once you start doing some of these arguments involving generalized indiscernibles, there are a lot of like sort of grungy details, which are really hard to absorb on the fly. And I think it's nice to have a text to look at. So I will try to be updating those, and I'll let you know when they're there. All right, so enjoy your Monday, and I will see you all Wednesday morning.